Hi everyone, so I'm Hugh Leather, not Bjorn Frankie, as you'll remember, and this is Distributed Systems. We're doing the Operating Systems lecture. I'm recording this from my living room, which is not ideal. I would much rather be talking to you guys directly, but that doesn't seem to be possible. So we'll see how this goes, and if it's terrible, well, I don't know what we do about it really. Okay, so today we are going to be talking about various concepts in distributed operating systems. But first we'll give an idea of what an operating system is. And then we'll look at networked operating systems, distributed operating systems, at virtualization, which is a technique used in lots of data centers and for other reasons as well. And then we'll finish off by talking about some of the current trends in distributed systems for operating systems stuff. Okay, so what is an operating system? Well, you all use one. You write programs that live in application space. And those programs make use of facilities provided by the operating system. So these will be user interface bits like the windowing system that you use and so forth. And those will call down into the kernel, into the core of the operating system through system calls, where facilities like control of the program, for example, yielding threads and so forth, input-output file systems, communications, and all of those things are provided by the operating system to you. And those in turn make use of the actual hardware. So the operating system sits between your programs and the hardware, making it easy for you to write your programs. The operating system provides a bunch of resources to you and manages them on your behalf. It also provides an abstract interface to those resources, so that you, as an application developer, can actually get access to them in a clean and sensible way. And then it makes sure that these resources are well managed. So it would be no good, for example, if you had, let's say, back in the old days, which I probably remember a little better than you do, but if you had a situation where you only had a single core computer, if multiple processes tried to run on it all at the same time without interleaving their time, or if memory was parceled out to the same bit of memory is passed out to multiple processes at the same time, they would overwrite each other. Although, of course, sometimes that is actually what you want, but most of the time you prefer not. So it manages these resources and makes sure that they are used properly. And it is this that allows you to have multiple processes in the same system, because otherwise it would be chaos and nobody would be able to work out what they should be doing. So for each of those different resources, the operating system takes a slightly different approach. For memory, the operating system will chunk up memory into pages, and it will give different pages to different processes so that they don't all try to share the same ones. You can look in an operating systems course. There's more to it than that, and that there's a whole bunch of translations going on so that your process thinks it's got a normal set of addresses, but actually they're spread around in memory. So the operating system maintains a list of unallocated memory and passes it out to people, to processes as they request it. And it knows what to do if it runs out, and it will manage, for example, spooling some of it out to disk so that more memory can be made available. It will manage the file system, making sure that if you try to read or write to a file, that you actually have access to that file. It'd be no good if you were using dice and somebody came along and was able to read your special password file or your diary or whatever it is that you've got stored there. And it will make sure, sometimes, depending on what is going on and what facilities your operating system actually provides, it'll make sure that only one process is writing to a file at once, or can do. And for the network, it will receive messages from the network card and send them down to the network card and make sure that they are ordered properly and that the network card doesn't get confusing sets of messages half delivered and so forth. Okay, so the way memory actually works, as I hinted at earlier, it's not quite as simple as it might sound. You'll see a lot more of this in an architecture course, so I'll only very briefly go through this. The idea essentially is that your compiler arranges a program's memory in a typical pattern. And the way this happens is that you have a text segment in your program which contains the code. You have another segment called the data segment, which contains your static constants and your globals. And then the rest of the space is divided into 2 bits, essentially, which is a bit growing upwards, which is called the heap, and a bit growing downwards, which is called the stack. You may remember from your compiler courses, if you've been lucky enough to do one, that memory in the stack grows downwards, and each time you make a function call, a little bit of extra memory is allocated onto the stack to represent the variables in that function call. And when you do malloc, memory comes off the heap to be able to do this. So these addresses that are virtual are how the compiler sees it. Well, in order to make sure that the memory, the actual physical memory that your computer has, doesn't get all, that you don't have to have a chunk given to the compiler and it sits there because the compiler's view of the virtual address spaces are huge. Then what happens is that actually that is broken up into a set of pages which exist on the physical memory, and the operating system maps those physical pages at physical addresses that it knows about into virtual addresses that each program knows about, and parcels them up so that although actually the way this diagram is done, it looks like the addresses are all contiguous, they aren't contiguous in physical space. They are all mixed about, or could be mixed about, so that the physical memory can all be used up efficiently. Okay. Another thing to note in operating systems is that there are 2 modes of operation. There is user mode and kernel mode. Now, in kernel mode, the difference between these two is essentially that in user mode, there are only so many things you are allowed to do. There are bits of memory that you are not allowed to touch. There are facilities that you are not allowed to go and mess with. If you want to access them, you have to make a system call going into the kernel to make sure that you use a set of allowed interfaces that stop you, for example, reading the memory of another process without permission, or going in and seeing files that you don't have access to. So when your user process is busily doing some computation all in its own space, that's fine. When it wants to do some I/O, for example, then it will make a system call, and this will change a bit, and then the code that goes on after that, and you can't change that bit, this is done with protection, and then from there on you'll be able to be in kernel mode, and it will enable you to execute the system call which does the protected code, and when it returns back out you'll be in user mode again. Behind this split between user mode and kernel mode is that the operating system can allow the processes to be completely unaware of what else is going on around them, and it will present to each process a view of the world which looks to that process like it is the only thing going on. The process doesn't need to know the details of the hardware if everything is well done, and they can know about each other if they need to, but if they don't need to, then they don't need to know anything about what else is going on. The idea being to make the job of the application programmers as simple as possible. So concurrency is managed by two or more methods in the operating system. The first is that there are processes. So each process gets its own address space, its own virtual address space, and a whole bunch of other resources allocated to it. And it cannot write to other processes' memory and so forth. Now, this is fine as far as it goes, but it makes parallel programming rather difficult, because you would kind of like to sometimes be able to share the memory and be able to write things to other concurrent bits of program. And you would also like not to necessarily have to pay the costs of having your entire address space separated, and when execution is swapped to a different process, have to swap all of that state back in. So instead, there are threads, which were invented a long time ago. And they're essentially very lightweight processes. The idea being that they share the same address space and other operating system resources, meaning that it is possible to switch execution from one thread to another in very many fewer instructions and clock cycles than one would normally have to do. So you can have one process owning one thread, or one processing owning multiple threads, and similarly you can have multiple processes of both types sticking around. Because the amount of state they have to them is much smaller, they can be created and destroyed much more quickly. The resources that they have can be, they're a small little bit on a thread table, and they need a little bit of space for their stack, and away they go. That means that your system can be much more responsive, and creating things is much easier. They can share resources amongst each other, memory being perhaps one of the easiest of these to see, in that by sharing an address space it makes it much easier for them to communicate, and again you don't have to swap out the page table. And because you've already got this, they are much more efficient. So this is what we tend to use in multi-core systems. Lots of threads running in parallel on different cores. So the slides then move away from talking about general operating system concepts, and we now look at networked operating systems. Most operating systems these days are networked. I think you have to go back quite a long time to my day before there were lots of computers around which didn't have any networking cards in them. These days pretty much everything does. So a networked operating system knows that there is such a thing as a network, and every node has some operating system running, because there's usually too much complexity in the hardware, etc., for them not to have a network. So the nodes manage their own resources, and they can communicate to processes on other nodes by saying to their network card, go send a message to somebody else, and you can do some procedure calls on other machines, or send messages, or do whatever it might be. So the way that this is typically done is by using IP addresses and port numbers, etc., which allow you to have a way to describe whom you wish to communicate with. So if you have an IP address and a port number, then you can try and talk to that machine on that port. There are a few other ways of doing it. A process can't request resources on a different computer, in general at least. And if it wants to do something on a different computer, it has to send information to that, send a request to that computer, requesting that it do that job for it. Actually, this is not entirely true these days. There are scale-out NUMA devices where it is possible for one machine to directly control the memory of another, but without the operating system being involved, and just using the network card on the other device. But these are slightly esoteric, being used in data centers for really efficient things, a little bit more difficult to program than normal stuff. The idea behind these networked operating systems is that if you want to do any distributed computing, you have to work it all out yourself. There's pretty much no help from the operating system. So here is a picture showing the things we've just been talking about. And this is the kind of stuff that you might see on a Windows environment. We've got some Windows servers that might actually be available for other machines, a bunch of clients, networking devices, a bunch of different applications and so forth, all managed by, in Windows, some Active Directory which allows you to go and make queries about what facilities are out there on the different networked computers that are there. That's Windows anyway. By contrast, a distributed operating system is one where a whole bunch of different computers appear to be like a single machine, or at least a single operating system. And here, the processes don't need to know specifically what other computers there are. They don't need to talk about IP addresses and send requests. They just act as if they're running on one big machine, and the distributed operating system will work it all out for them. So if a process wants input and output from the hardware, it will ask for it, and it doesn't need to know which actual computer it will be on. If one process communicates to another, then it doesn't matter whether they're on the same computer, the operating system will take care of that all for it. Which sounds great, right? I mean, this sounds like a good thing. The process may be running on a different computer from where it started. It may get shifted over, moved around. Again, the process should not have to care. This all sounds very nice. The system is all hidden. The distributed bit of this is all hidden from the processes, and it should make life very easy for the application developer. Okay, so here we see a picture, actually not really of a distributed operating system, but more of distributed applications running on a networked operating system. And here, what happens is that each of the machines you've got connected by a network has networked operating system services, and you probably use some middleware that understands the networked operating systems for you to be able to enable your distributed application to be written simply and communicate over the network. So what kind of things might the middleware have? It might have, for example, facilities for you to do leadership elections or so forth, or some of the things that we've talked about in previous lectures. So this would be using distributed applications on networked architectures, networked operating systems. By contrast, a distributed operating system looks a little bit simpler to the applications in that there appears to be no networking needed. It understands for you where all the actual processes live, on which machines and so forth. So in a distributed operating system, you have one interface to all of these resources, which is great. And you can make a program that can be run in a distributed fashion, and that's great too. And it sounds like this is exactly what we need, because everything should be easy. Why aren't they all over the place? Well, there are a number of problems. One is that if your network is partitioned, in other words, if it is separated into two sets, then how you handle that can be rather difficult, because the different sets, the subsets of your network, have no way of knowing about what's going on the other part of the network. And this means that if you've got some things that have gone over there, you can't get access to them, you don't know how to handle it. It may actually be that you need quite a lot of application-specific stuff in order to be able to handle this kind of thing. So if you had two processes that started on the same computer, A and B, two processes A and B that start on the same computer, and then the operating system moves one of them to a different computer, and then they communicate a lot, well, if the operating system hasn't managed this for you to put them back onto the same machine, then you're going to end up with a very slow system. Often, having the application programmer knowing more about it is the right way to go. And although it would be great if there were ways to provide hints, etc., to distributed operating systems, it turns out that in general people have basically figured that it's easier to handle the concurrency through middleware than it is to have the entire operating system be distributed. In addition, you have to access resources that are off-site, not as part of the distributed operating system. And so at that point, your distributed operating system is still network aware. And your applications that you write still have to be network aware. When you have new nodes added to a distributed system, then they have to be brought online and new connections made, and your program has to be made aware of those in some way, and again it makes life a little bit difficult. And so the upshot of this is that distributed operating systems tend not to actually help you very much when you are writing distributed applications. So yes, for these reasons, because it's very difficult to work out what failure means, and to design an operating system which is tolerant to all the different types of failures you can get, because the different ways in which people would like to write efficient distributed computing, there are too many possibilities. It's impossible to design an operating system which takes care of all of them. And consequently, it's better just to let the application programmer deal with all of this for you instead, well, by themselves. And the operating system, if it provides a bunch of facilities, can make that as easy as it can without claiming to take care of all of it for the programmer. So when we compare networked operating systems versus distributed operating systems, we find that we don't get many distributed operating systems in regular use. There are lots of operating systems, lots of networked operating systems. In fact, pretty much, as I say, pretty much every operating system is networked these days. And they all provide the communication facilities that you would expect. The software manages how to execute distributed computation. It gives much more flexibility, and the application can handle any failures. The operating system continues doing all the things like managing the file systems and so forth, and people seem to be happy with this as opposed to using distributed operating systems. And what people do to make their lives easier is to use middleware that provides facilities for distributed computation. For example, Apache Ignite provides synchronization, mutual exclusion, failure detection, and so forth as a set of services that you can use to build your application. And these then become distributed applications, and your needs are met by different things that you can pick up from different places. So, now that we have covered some of the differences between networked operating systems and distributed operating systems, I'm just going to move a little bit to talk about virtualization. So the idea behind virtualization is that we essentially simulate an operating system inside another operating system. And this will give us abilities to do things that we couldn't otherwise have had. So a virtualized operating system runs inside another one and may not even know that it is being run inside another operating system. And we can do lots of things to it, like move it from machine to machine, save and restore its state, and do other things that are rather useful. And in addition, because it's running virtually inside, we can run multiple different operating systems at the same time on a single computer. This allows for actually running Windows next to Mac or to Unix and so forth, if one would like to do that, but it is possible. And the resources of the machine, of the single actual physical machine, can be shared amongst different virtual machines. There are typically two types of way this is done. There are hosted virtualizations and hypervisors. So the hosted one installs the virtualization layer as an application on top of the operating system. So this means that the virtualization thing is pretending to be an operating system, and anything it tries to do has to get translated down into normal system calls by an application at the user mode level. Hypervisors, on the other hand, use specific hardware capabilities that most modern x86 systems, for example, today provide in order to make things fast, so that they are most of the time running directly onto the bare metal, onto the actual hardware underneath. And a set of facilities provided by x86 machines enables you to swap in and out and do various bits so that the virtual system is running as fast as it possibly can. Why do people use virtualization? Well, it allows you to sandbox, for example. This means that you can create a virtual operating system inside your server, have that run. If at any point you don't like what it's up to, you can stop it. You can stop it having access to anything that you normally wouldn't want it to have access to. So if, for example, you are Amazon and you're providing compute time to third-party clients, they can run something on your servers in a sandboxed virtual machine, and you can make sure that they don't have access to Jeff Bezos's personal accounts and so forth. It allows you to do testing and backup. And by backup, you can, for example, stop the virtual machine at any point, save its state, and reinstall it later. This is very useful for fault tolerance. If something goes wrong, if one machine dies, but you've got a backup, then you can respawn it later, either when you've fixed that machine or when you've moved it to a different machine. And you can migrate it. So if you discover that one machine is heavily overloaded, you can move a virtual machine from one machine to somewhere else. Or if something else comes along that's more important, you can move virtual machines around, and everything should work without the processes running on that understanding that they have been moved. So virtualization is quite common inside data centers, and if you use AWS or anything like this, you'll find that you are actually being given virtual machines to play with instead. So here we go. If we consider a server farm, then you've got lots of different servers running around, and instead of giving, well, this is essentially what places like Amazon and Azure do. So they've got lots and lots of physical servers, and instead of giving users actual machines, they give them virtual machines instead, enabling them to move things around and to have more control over it and to understand more what's going on, and for all those reasons that we've been through already. This virtualization gives the owners of Amazon and of you much more flexibility in that you can install different things on your operating system without messing with the host that you are running on. And they can have multiple users running entirely sandboxed things on the same machine. Turn them on, turn them off, back them up, and move them around. So the problem with this, though, is that if you are doing distributed computing where there is significant communication between your different processes, different distributed processes, and you're doing it in a distributed fashion to achieve the highest computation, the high throughput computationally that you can, then running virtualized stuff is not great because there is an overhead of running things on VMs. So virtualization is most often used when you want things like web services that can be restarted and respawned, and it's not so much about getting intensive computation, it's about being fault tolerant and having availability and so forth. So just to finish off, the current trends that Bjorn's slides have talked about are also to talk about mobile systems, where there are lots of different mobile systems competing to see who is going to be boss. We need for the operating system to take account of the fact that it's running on a mobile. What does this mean? It means that your networking might be less reliable, in that sometimes people will be going out of area or networking connections will be dropped or suddenly become slower. And also that because you are running on a battery operated system, that one has to be very careful with the resources that you use, that you don't drain the battery too fast. These operating systems also have a different style of user interaction, and they need to take much more account of how the users interact with them because they aren't plugged into the mains all the time. And individual users now have multiple devices, so these operating systems also provide capabilities for users to synchronize their data across different devices. As we go forward, these slides are a bit old, but there are more things like, for example, working out how to do machine learning at the edge so that some bits of machine learning inference and training are done on your device, whilst more complicated things are shipped off to some data center somewhere. And how to do distributed computing across mobile systems is something that people are looking at. So there we go, a brief introduction to operating systems stuff. Actually, there's more slides. So there are also sensor networks. These are very small devices on the Internet of Things, which sometimes are really, really tiny, powered by things like TinyOS, which is not a full-featured operating system. It connects tasks together and does a little bit of networking between these things. A few other of these tiny little sensor network operating systems. They are super low power, where they've got a tiny little battery often, or maybe just a couple of AA batteries, but they would be expected to run on those perhaps for years. So they really do need to be low power. And under those circumstances, the difficult things become, if you can only turn on once an hour, how do you make sure that you communicate to somebody else who has only turned on once an hour when you also haven't been able to share a clock? This makes life very difficult for these very small operating systems. So you need specialized systems to process and handle all this data, and to work out how to send things around and to aggregate the things and to collect all of your sensor information, which is why you have them in the first place. A little bit bigger, we have embedded systems. So these would be operating systems sitting in your fridge or your toaster, though God knows why anybody would want an internet-enabled toaster. You can actually get them. Obviously, they're not Red Dwarf fans, but never mind. So the embedded systems in everything, including your car, which also sounds horrific, but there we go. And they need to have some operating system and often some distributed computing to communicate with your phone and let you control your heating and so forth from your office. And they often need to be low power, low resource, because they're typically quite cheap, and one needs to make them as cheap as possible. Okay, there we go. That is the first of today's lectures. We'll see how it goes.